Good morning, everybody. Today we're going to be talking about one of my favorite architectural ideas, like things to wrestle with when developing your web application, and that is how to choose your database technology for your web app. For those of you who don't know me, my name is Howie Reith. I'm a software developer. I am enthusiastic about learning really great things about code and teaching those things to others. If you'd like to reach out to me, my email address is howard.reith@gmail.com. And if you have any questions about this presentation or others, feel free to contact me there or leave comments in the video here. As always, there will be a link to the GitHub repository that holds this PowerPoint presentation and others in the description. So let's talk about the purpose of this video. We are looking for a means of making architectural decisions for our web applications concerning how we want to do data storage. For this, I want to basically indicate what my driving principle for this is. And in science, you've probably heard of the notion that the simplest explanation is usually the correct one. Now, that is used descriptively in science. I am going to put forward that prescriptively when it comes to software engineering, that the simplest solution is usually the correct one for any problem we're trying to solve. Now, I want to clarify on that. This is the simplest solution that meets our needs. Obviously, you can't just use the tiniest data structure for a really complicated problem. But generally speaking, you want your solution to be no more complex than the domain of that the solution is trying to solve. So why wouldn't we? Well, anything that's excessively complex is going to make our application run more slowly, more difficult to comprehend for any new developers who join the team, and more difficult to change and maintain in the long run. For someone who was way smarter than me but said something similar, the name of the game is congruence. The techniques you employ had better be consistent with the intrinsic complexity of the problem you're trying to solve. Now, why am I harping on this so much? Well, with many technologies, and with databases in particular, there's no shortage of people out there who say, this database technology is the best one. It is the one that solves every single problem. You should just apply it to absolutely every single use case. And that is not the case. Every single thing in software engineering is a trade-off. You'll have to choose between front-end styling libraries. Some of them are more complex, some of them are more simple, but you're going to have a trade-off there. So essentially there is no silver bullet. There is no single best technology. What you need to do as a software engineer is take a look at any given technology and evaluate the degree to which it fits your use case. What is the simplest technology that I can employ that solves my particular use case, that has very good benefits for what I'm trying to do, and the liabilities of it are not particularly relevant? That is the problem you're trying to solve, and when you are architecting the solution, those are the sort of judgment calls you need to make. So here are some common threats to this philosophy. Company X uses this tech, and they're successful, so we should use it too. I'm used to this technology, so we should stick with it. I talked to the salesman, and he thought it was really, really great. And if we don't use the newest tools, we're going to fall behind. Your sort of resume-driven development, right? These arguments are ubiquitous in our profession, and you need to avoid them. You need to be resistant toward them, because if you're not, you are going to write suboptimal software. Okay, that all having been said, let's talk about one of the big factors for how we evaluate a database technology and our use case, and that is the CAP and PACELC theorems. So CAP theorem is also known as Brewer's theorem. It was conceived in 1998 by Eric Brewer of Berkeley as a response to the rising web scale problem. There's a formal proof for this that is going to be linked inside of the bibliography if you want to read it. But in essence, the theorem states, in the event of a network partition, distributed systems can have only 2 out of the 3 CAP attributes. And those attributes are consistency, availability, and partition tolerance. So consistency concerns whether all nodes in a distributed database have the same data at all times. So imagine you have a database with a whole bunch of nodes in different states across the United States. And so these nodes would need to sync up every time one of these nodes gets updated with new information. That is, if you are valuing consistency. If you're valuing availability, it's the ability of the system to remain operational in the event of a failure of any of its constituent components. So if one of your computers and one of those nodes goes down, how does the system behave? Do the other nodes still respond, or don't they? And partition tolerance is the ability of the system to continue when a server communication breakdown occurs. So the network connecting these various nodes has a problem. How does your system behave then? Here is just a little diagram, just illustrating you cannot have all three of them, but you can have any two at one time. And I just want to also note, you can have only one if that's what you decide, like you really, really care about consistency. You can forego the other two. That is acceptable and actually not particularly uncommon. So here are some examples of prioritization. If you have consistency and availability, this is your classic case of your database is only in one computer. It is consistent with itself and as available as possible, but if the internet goes down, it's going to eliminate the system. If you have consistency and partition tolerance, you have multiple nodes distributed around, but they always require syncing up before accepting any requests to read or edit, otherwise that will not be allowed. Or if you have availability and partition tolerance, you have a database across many nodes, and it will always respond with whatever data it has inside of it, regardless of any failures to communicate, whether those failures are caused by a node going down or a network error. If it can respond, it will always respond. Any decision you make concerning the CAP theorem concerns what you are going to forego. Which of those three attributes is least important to you? And furthermore, since availability and partition tolerance are pretty similar, they both concern how your system behaves when you aren't able to get a response from a node, most of the time what you're really choosing between is consistency and availability. So let's do a little quiz. Assuming partition tolerance is a requirement, identify the appropriate CAP attribute, consistency or availability, to prioritize in each of the following cases: financial transactions like in PayPal, social media applications like in Facebook, content management like, say, WordPress, like website hosting or something, or online sales inventory like Amazon or Alibaba. Feel free to pause the video and think about these, and then I'll share my thoughts right after. Alright, let's go over this. So, in my opinion, financial transactions, pretty classic case of prioritizing consistency. You don't want to be starting some sort of like withdrawal in one place and somebody else withdraws from the same account somewhere else and the account is overdrawn, or there's some issue with transferring money, or someone loses a bunch of money or gains a bunch of money inappropriately, something like that. So you want to make sure that all of your nodes are consistent with one another anytime you're dealing with money. So I would prioritize consistency. For social media applications, I'd probably prioritize availability. We care more about our users having a positive experience than we do about them having the most up-to-date information possible. So if Becky in California updates her status and Bill is looking at Facebook in Massachusetts, do we really care if Bill has the most up-to-date version of Becky's status? Probably not. It's probably okay if he doesn't even see it at all for several minutes. So, hence, availability is more important in that context. Content management, probably also going to go with availability. Somebody updates their website, obviously we want that to sync up, but it's probably the case that they would rather have their customers be able to see a website, even if it's an old version, than get a 404, right? So probably want to do availability for content management. And for online sales inventory, you can go either way here. If you're working for a pretty small company and you have limited inventory, you probably want to do consistency. You don't want to be making promises that the company can't keep because the database didn't update quickly enough. But then again, if throughput isn't a problem, if you have lots and lots of stock like in Amazon and Alibaba, maybe you can do availability, because then you're thinking like, oh, if this takes too long for the transaction to go through, or if the transaction times out, then I'm going to be losing customers, I'm going to be losing sales. Well, then you want to be prioritizing availability. Let's move on to PACELC. So the PAC of PACELC are the same as the CAP and CAP, but PACELC introduces two other concepts, latency and consistency. So note with CAP, we were only concerned with what happens with a partition, with an actual failure of the network. With PACELC, we are evaluating what is happening when the system is behaving correctly, but perhaps a little bit slowly. How do we want our network to behave in that environment? So in option 1, on every request, you block all other reads and writes until data is consistent across all nodes. This is a requirement for transactions, and it is extremely complex to pull this off inside of a distributed network. Option 2 is to respond to every request with available data, regardless of whether it is stale, and we're going to trust that eventually the data becomes consistent. This is simple and fast, but it can return incorrect data in the event of high latency. So here, let's do another quiz. Your team has decided to prioritize response time over consistency. What are the possible results for the following sequence of actions? A user adds a book to the catalog from the Add Book page, and the user immediately views the catalog page to find the book. Well, simply enough, in this case, there is the possibility that the user will look at that catalog and it will not yet have been updated. They might have updated one node, but they could be retrieving their view from another node and that node has not been updated, but it will respond immediately. Okay, second question. Your design team has prioritized consistency over response time. What are the possible results of the following? User A in the US performs a mass update on books by an author. User B in Australia requests all books by this author microseconds later. Well, in this case, there is the possibility that user B in Australia is going to get a 404, is going to time out and not be able to view these books because they are being updated by user A and all of the nodes are syncing up. On the other hand, if they sync up quickly enough, perhaps user B will see all of the updated books immediately. It could go either way, but that is the risk when you have prioritized consistency. So moving on, let's talk about acid and base. So acid and base are design philosophies at opposite ends of the consistency and availability spectrum. Acid stands for atomicity, consistency, isolation, and durability. Base stands for basically available, soft state, eventual consistency. Take a guess which one came first. So atomic means all operations within a transaction succeed as a whole, or every operation is rolled back, basically transactions. Consistent means that these transactions always begin and end in a consistent state. So you have a bunch of constraints that you apply to your database, and if these constraints are not met, then it does not pass an ACID transaction requirement and it is rolled back. Isolated means every transaction is necessarily isolated from all others, ensuring that consumers are guaranteed never to receive data in an intermediate state. So if you have multiple people who are engaging in transactions at the same time, none of these should be interacting with one another, and if they are addressing the same account or whatever, they're going to have to wait. And then durable means that every single transaction is persisted to the hard drive. So in an ACID system, you are prioritizing consistency above all other concerns. Like, you are only getting one of the 3 CAP options right now. You are getting consistency, and that is the most important thing. Since everything has to sync up, there needs to be some really complicated locking mechanisms. Once this part of this database is updating, that needs to tell every single node, hey, don't let anybody touch this section of the database. I'm updating it right now. And generally speaking, horizontal scaling and redundancy are very difficult to do in an ACID system, and they're resource intensive and complex for a similar reason. You need to have a lot of communication between all of these nodes to lock everything, to update everything, and so on. So yeah, it's definitely a challenge. So now let's talk about base. Basically available means the system will always respond to requests. Soft state means that it writes queues in memory and then writes them in batches rather than each transaction. And eventual consistency means it is assumed that all replications will become consistent eventually. We make no guarantees that this will happen. So since in a base system, availability and performance are prioritized above consistency, data loss is possible in a system failure since you're storing stuff in memory. It's possible that if the system goes down, you have lost the stuff that's in memory. It has not been persisted to your hard drive. It is very easy to horizontally scale and replicate a base system because you don't have to do all of that syncing up. That just occurs as it can. And users will always get a response, but the data may be stale. So let's do a little quiz on ACID and base. So consider you have a banking system that's maintaining financial accounts, and you have SQL code that's transferring money between these accounts. So in our SQL, we have account 138 transferring $1,000 to account 139. Now assume there's a system failure after that first update. What is the result of a database supporting ACID transactions? And then second, what is the result in a database with a base model? So if we're doing ACID transactions, we are going to do our first update, subtract $1,000 from the account. We're then going to have a failure. Thus, that update is going to be rolled back and the $1,000 is going to be put back into the account, and the user is probably going to receive some sort of 400 error or 500 or whatever the source of the error is, and be informed that the transaction did not go through. In a base model, that $1,000 is going to be removed, and then there is a chance that the $1,000 is not added. It probably will not be added, and whether or not this is a problem is going to be a function of what the error is and whether it prevented the $1,000 removal from being persisted to the hard drive. So if it was persisted to the hard drive, the employees at the financial institution are going to need to go in and manually adjust the database. If it was not persisted, it might be okay, but yeah, that's the danger of a base model. That's why we probably wouldn't want to use it for a financial system. So, to summarize, by the CAP theorem, with any distributed database system, you must choose between consistency and availability. And by PACELC, you must choose between consistency and availability in the event of a high latency situation. ACID systems strongly prioritize consistency, and base systems strongly prioritize availability. Alright, so now in the next section we're going to be talking about the many different types of databases. Feel free to take a break right here. This is going to be pretty in-depth, and I'm going to be throwing a lot of information at you. So feel free to pause the video, take 5, and come back, and then we will delve into this topic. So, the 5 genres of databases. I'm going to start with a little caveat. Obviously, databases are a pretty diverse technology that have existed for many decades now. These 5 genres don't account for everything, and even within these genres, there's going to be a fair amount of variation. I am categorizing things into these 5 genres because they are generalizable enough that I think we can use these as useful categories to make evaluations for our architecture. Feel free to talk about that further in the comments. I'd be happy to talk about it, but for our purposes, I think these are useful categorizations to make. Alright, so Relational Database Management Systems, RDBMSs. They are by far the most popular database style in use today. They are set theory-based organizations implementing two-dimensional relations that you can think of as tables, with attributes contained in sets of tuples, which you can think of as rows, and these attributes are defined by a header tuple, which is basically a column header. Relational databases are built on relational algebra, with a combination of selections, projections, Cartesian products, and more. And by the way, it is their origin in relational algebra that is the source of the term relational database. It is not because tables relate to one another via foreign keys. They are interacted with via structured query language, SQL, and data values are enforced types and may be numeric strings, dates, blobs, or in some databases like Postgres, user-defined types. Now, They feature a capacity to perform joins, and in my opinion, this is probably the greatest appeal of relational databases. Through joins and a few other options, you are able to write pretty much any query that you will ever need, regardless of the data structure that you have organized inside of the database. They are very efficient at managing blocks of data and disk reads, which allow for fairly fast lookups. However, this can only get so fast. For example, if I were to have a database of holidays and I were to try to find the holiday named Star Wars Day, you need to scan every single row to find it. Now, you are able to do some amount of indexing on columns for more efficient searching, but this will still be slower than such reads would be in other database types for this purpose. So for the purpose of our discussion, our primary example is going to be Postgres. Obviously, there's a lot of relational databases, but Postgres is basically the big workhorse of the web development world. It is the most popular tech. And in terms of CAP, relational databases prioritize consistency. So the strengths. They have years of research and production use across nearly every field of computing. They have very flexible queries. No matter what your model is, you can devise a combination of joins, filters, views, and indexes to get what you need. These schema constraints make enforcing data regularity an easy task. There are many open source options. There are many business concerns like budgets and other shipments that are easy to visualize in a sort of table format. And they have nearly uncontested dominance in ACID transactions. But weaknesses. They're very difficult to scale horizontally, as relational databases do not partition easily. If your data does not fit a defined schema, managing it is going to be a nightmare. Yes, you can do all of these complicated queries to get what you need, but you're going to have to. If you do not know your schema at the start of your project, this will be a tremendous complexity liability for this reason. If your data is deeply hierarchical, querying that data will be exceedingly complex and inefficient, because you're going to need to do so many joins and so many links between different tables. If you do not require the wide variety of querying options supplied by the relational model, accessing and updating your data will be slower than a simpler solution can offer. Let's talk about a simpler solution. The key value store. This is the simplest model that we will cover in this presentation. Essentially, it is just pairs of keys and values. It is a hash table data structure. For if you are familiar with how a hash table works, or say an object in JavaScript or something like that, you understand how a key value store stores its data. Some key value databases permit some complex values like hashes or lists, and some allow iteration through keys, but these are bonuses, not universal across the genre. They tend to be poor at linking data together due to the lack of foreign keys, and they tend to reside in memory, writing to disk only periodically. They are thus extremely performant, but a bit risky and a bit lacking in queryability. Obviously, if your system goes down and it's stored in memory, you're going to lose anything that wasn't persisted to disk. And you can't query it like you can with a relational database. You are basically trying to access the stuff that is at a key to get its value. So primary examples for our purposes are going to be Redis and Riak. And the priority for key value databases is availability. So let's talk about Riak. Riak is a distributed key value store where values can be anything from plain text to JSON to video clips. They support all sorts of different data types. They utilize an HTTP interface to interact with it. They are extremely fault tolerant. Their goal in designing Riak was that you could just put up the database and go to sleep at night. You're very unlikely to be called into work because of a database crash. They have links metadata, which allows association between keys to a limited degree. You can link walk between keys and do a little bit of querying that way, though it's not super powerful, but it's something. And you can also add some arbitrary metadata using the xRiak meta header prefix that adds a little bit more queryability. And one of the really cool things about it is you can change your CAP requirements on a per query basis. So if you want this particular query to have consistency, then and lock everybody out, you can do that. Or if you want to prioritize availability, you can do that. So now let's talk about Redis. Remote Dictionary Service. It's a distributed data structure. allowing a variety of data types including binary search trees, hash tables, sorted sets, and a lot more. It is one of the fastest databases in existence, with fast reads and even faster writes. And most commonly, it is used as a secondary database for tasks in which speed is essential, like as a caching layer. So if you can imagine, you have a relational database that has a really complicated query that a lot of users are frequently making. What you can do is you can make that request and then cache it into your Redis database, and then anytime somebody comes in to make an additional query with that exact same query, you can just give them the response you have cached, rather than having to run the whole query all over again, probably giving you a big performance hit. Very, very valuable for that purpose. So the key value store strengths. Speed. Nothing is faster. Horizontal scaling is easy, simple, and reliable. The more developed options support some complex data structures and the ability to deep dive into hierarchical data. They are ideal as a companion database to speed up certain processes. It is simple to distinguish the session data of different users. So one of the common use cases for Redis, for example, is to manage when users are logged in and logged out. And one of the reasons that this is very easy to do is you have your database here, user logs in, you create a new entry into that database, and as soon as the session expires or the user logs out, you simply remove that entry from the database. So it's very easy to keep track of these sorts of sessions simply by virtue of how the database works. Then with React in particular, you can change your CAP requirements on a per bucket or per query basis. Now let's talk about weaknesses. They don't have indexes and they don't have robust scanning capabilities, so you will have a hard time performing complex queries of your data. While some of them offer some queryability, this functionality should only be used for edge cases. If you are frequently finding yourself needing to look into the content of your data, you're not just saying, hey, I want the value that's at this key, you probably want a different database. Since they lack a rigid schema, it is very difficult to enforce data consistency. You're going to need to do that in your pre-processing. And since it typically resides in memory, in the event of a hardware failure, you risk losing any data that hasn't been persisted to disk. Alright, moving on. Let's talk about column-based databases. So imagine you have a two-dimensional table, like you do with a relational database, and imagine how you might store that data in your computer's memory. You might envision each cell in a row being adjacent to each previous cell, perhaps organized as a list. So in relational databases, that's not far from the truth. But imagine, instead of putting all of your rows in there, imagine if the adjacent bits of memory inside of your memory chips were the actual columns of the database. So each next item is the next entry in the column as opposed to the next entry in the row. That is how a columnar database is storing its data. Now, that might seem to be a trivial difference, but the implications can be pretty remarkable. It makes adding and retrieving columns of data extremely inexpensive when compared to other designs. Each row can have its own different set of columns, or none, allowing your data to remain sparse without incurring a cost for null values. Also, if you need to retrieve an entire column, that's going to be lightning fast, versus if you're doing that with a relational database, you're going to have to iterate through every single row in order to retrieve all of the data in a column. So our primary example for this presentation is HBase, and it prioritizes consistency. So when do people use columnar databases? Usually in situations where you want both consistency and the ability to quickly retrieve large groups of details about subjects, rather than information about the subjects themselves. So the example I like to use for this is, let's say you have a hospital database. When you are retrieving information, like let's say you have patients and a whole bunch of information about the patients, including different appointments they had, different diagnoses they had, and so on. When you are retrieving information from this database, do you usually say, give me everything about this patient? Well, if you do, then you probably want something like a relational database, because that's a pretty standard use case for that. But let's say you're doing data analysis. You want to do an analysis of every single time somebody was diagnosed with a certain illness. So you want to look inside of the illnesses column and grab all of that data. Well, in that case, it would probably be more performant for you to have a database that's organized by columns. You don't necessarily care about the patient who was diagnosed with this. You just care about the fact that it was diagnosed and any related information to that diagnosis. That is the use case for a columnar database, usually in the context of data analysis and research. So what are the columnar strengths? They offer the power of complex querying in a manner well suited for massive data analysis. They make strong consistency guarantees. Horizontal scaling is cheaper and simpler than relational databases. They contain built-in support for compression and versioning, which makes it exceptionally well suited for datasets that are highly textual and change over time. That is HBase specifically that has that, by the way. And HBase can also prioritize availability to a degree with cluster-to-cluster replication, providing some limited CAP flexibility if you need it. Weaknesses. What makes a column-based database worthwhile lies in the ease of querying its data. And your ease of querying that data is going to depend on your data model. You must carefully consider your schema up front and be sure the structure is exactly what you need it to be to run your queries. You thus need to know a lot about your use case before you begin. And if you get it wrong, life is going to suck. It is thus a very poor choice in the context of agile development. HBase is difficult to administrate. There's a high learning curve, and not many people know how to use it well. HBase doesn't support data types. All field values are uninterpreted arrays of bytes, and it offers no indexing or sorting except by row keys. I will make this very simple for you. If you do not know beyond the bottom of a doubt that you need a column-based database, you do not need a column-based database. Okay, this is a complicated system. It has a very, very narrow, appropriate use case scenario. But in that use case, it is very valuable, and it will make your life easier than any other database will. Let's move on to document databases. So they store data as documents, which are essentially hashes, or more directly, for our example cases, JSON-like objects. They have unique ID fields and values that may be any of a variety of types, including arrays and hashes. And due to their accommodation of many data types, they are extremely flexible, perhaps the most flexible, with a little competition we'll get over to shortly. Different databases take varied approaches to indexing, querying, replication, consistency, and other design concerns. We're going to delve into the two perhaps most popular ones here, MongoDB and CouchDB. So they are pretty similar in a lot of the ways they solve these problems, but be aware, document databases are a very varied genre. So not everybody is going to solve things the way these two databases do. Like I said, primary examples, Mongo and Couch, prioritizing availability. So MongoDB, the most popular document database at the moment. It stands for humongous. It is designed for scalability. Data can persist in a nested hierarchical state and allows ad hoc queries of that nested data. There is no schema, and documents can contain fields and types that no other document contains. It supports indexing of data, potentially speeding up queries, and thus hits a sweet spot between the queryability of relational databases and the distributability of key value stores. It is exceptionally well suited for web applications, presuming those web applications are using JSON. Basically, Mongo is designed for the web world. It is designed to speak JavaScript, so to speak. So, if you are doing the web app and you have an appropriate use case for Mongo, it is going to make your life a lot easier. Couch is also a JSON REST-based document DB, storing its data as key value pairs with many supported data types. While Mongo was designed for scalability, Couch is designed for survivability. It is built to weather even the worst network and system failures. It is uncannily scalable, both horizontally and vertically. You can have Couch running effectively on your phone, or you can have it running on your big, powerful supercomputer inside of your company's data center. It has an append-only storage model that makes data virtually incorruptible and easy to replicate, backup, and restore. It, however, does not support ad hoc querying. So, document strengths. It is schemaless. If your data structure varies, or if you don't know what your data will look like ahead of time, document DBs will be perfect for you. They support hierarchical data models that are easily delved into, and they map easily to object-oriented programming, especially when you're working with JavaScript on the web. They're easily replicated across servers when prioritizing AP, and they support SQL-like queries and also support indexing. Thus, if you are somebody who is accustomed to relational databases, but you are looking for something that supports more availability, Mongo is going to be a relatively easy switch for you to make. CouchDB is exceptionally well suited for hostile web environments in which network connections and systems are unreliable. It is basically a juggernaut. It will always live. Document weaknesses. If you need to enforce data consistency, this is the wrong choice. Document databases will basically accept any old value that you shove in there. So if that's going to cause problems for you in the long run, you're going to need to do a lot of cleaning of your data as it goes into your database. You need to store most or all of your data you'll be retrieving together in the same document. If you are finding yourself doing a lot of queries with data spread across multiple documents, it's going to be pretty slow and inefficient, and you probably want to be using another technology. While Mongo is flexible at the document level, it's built to handle very large data sets, so you need to be very careful when you are setting up new clusters and your overall structure of the entire system. For Couch's sake, the replications must all be the same. There can be no sharding in a CouchDB database. Alright, let's talk about our last genre, the graph database. Graph databases are based on graph theory, which is the study of mathematical structures used to model relations between objects. If you look back on our various databases so far, there's usually been an essential element to them. The relational database, it was probably the row or maybe the table. The document database had the document. The key value stores had the key value pair. For this, the relationship between the nodes is the integral element, not the node itself. These relationships are called edges. So imagine you are describing a family tree or some system with relationships to one another on a whiteboard, and you're drawing circles with lines connecting things. If you can represent your data in this way, it is a candidate for a graph database because that is exactly the way graph databases structure their data. The primary example we're going to be discussing is Neo4j, and it prioritizes consistency. So nodes on a graph database are similar to documents insofar as they exist as hashes with properties that are key value pairs. Graph databases are schemaless and capable of representing highly variable data, perhaps even more so than document databases. When querying, what you're doing is you're usually starting at a node and running along the nearby edges. For example, if I had a family tree app and I wanted Henry's family, I would collect all of Henry's family members with a constant 0,1 asymptotic complexity, while other databases would need to run search algorithms. And the reason why it is able to do this is essentially you have the element that you are looking to do, and you have the address of that when you go and get it, and then it has pointers to all of the related elements that you are going to. So everything that you need to access related to this thing that you're searching for is immediately stored next to the thing you're searching for. So you will never be more than one step away from what you need to get, assuming that these are the sorts of queries you need to be running. Thus, if your use case involves collecting related data in this way, you will not find a faster database structure than a graph database. So, strengths. They are typeless and schemaless, capable of modeling nearly anything, even more so than document databases in many contexts. Unlike join or MapReduce operations, GraphDBs traverse edges in constant time, and no matter how large your data becomes, traversing from node A to node B will always be a single step. They are unbelievably fast for this purpose. Visualizing the data is object-oriented and intuitive. I don't know about you, but I have a very easy time imagining these sorts of circles and bars connecting them. I have an easier time with that than I do with a spreadsheet, and I have an easier time with a spreadsheet than I do with a JSON blob. So that's just me, but I find this data very easy to visualize. Neo4j does support ACID transactions. However, I would not recommend going to a graph database simply because you need ACID transactions. So some graph weaknesses. Nodes are all interconnected, thus sharding is impossible. You can replicate across multiple nodes, but if your data grows above the max capacity of your tool, which is 34.4 billion nodes and edges for Neo4j, you're screwed. This is unlikely, but it is possible if you are working with a very large data set. Neo4j is not partition tolerant. It prioritizes consistency. And traversing along edges is the key to success with a graph database. If your queries more frequently involve retrieving data from unrelated nodes, it's going to be pretty slow. So now let's do a final quiz. In this quiz, I'm going to ask you 10 questions, and your job is going to be to determine which database genre is most appropriate for each of the following use cases. Now, we're going to go over all of the answers at the end, so feel free to grab a piece of paper and write down your thoughts for each successive one, and then we'll go over it at the end. So question 1. An online banking application that will keep track of client accounts and perform financial transactions. Question 2. A dating site in which users will rate how attractive they find other users, and the application will make recommendations for dates with users similar to those whom the user has rated highly. Question 3. An application for a warehouse used to keep track of inventory. Question 4. A scientific database in which biologists will catalog the characteristics of new species of microorganisms they discover. What qualities they need to record is not known ahead of time. Question 5. A messaging app. The only information that need be stored is the timestamp, users involved, and the messages. Conversations will be held in real time. You do not expect to need to search the content of the messages. Question 6. A large e-commerce website with customers all around the world. Question 7. A search engine that will index all of the websites on the World Wide Web. Question 8. A tool for applying for research grants. The requirements for each grant application vary from offering to offering, especially between different grantors. Users will occasionally want to run analyses on and retrieve information from their past applications. Question 9. One of the largest social networking apps on Earth. Most interactions are short, less than 180 character messages, but the dataset is so massive that sharding will be necessary. Basically, when I wrote this, I had in mind Twitter. Question 10. You are the lead engineer at a contracting firm that builds software for a wide variety of clients. Everything from financial firms to dog walking apps to cloud video storage. Identify the best general use database tool for all of the product teams to use. Alright, let's go over the answers. So for question 1, this was the online banking application. This is the classic use case for a relational database. We need ACID transactions and enforcement of account schemata. Pretty cut and dry, in my opinion. For question 2, the dating site. This one calls for a graph database. The relationships between the users and the magnitudes of those relationships are the crux of the application. We want to be able to collect that information quickly by traversing edges, then that'll allow us to show what our recommendations are and what our connections are to our users in a very fast and user-friendly way. So question 3 was the warehouse application. I would say a relational database. It's a little bit less cut and dry than the banking application, but we probably want to have ACID transactions to prevent the warehouse from making any promises it can't fulfill or losing track of inventory due to system failures. A defined schema will also help ensure discipline in record keeping. So question 4 is a scientific database. This one I thought a document database would be most appropriate. We lack foreknowledge about the attributes we will need to be recording, and thus we will not be able to really clearly define columns for our relational database, so I think that's going to be a bad choice. And there's a high likelihood that what will be recorded will vary from entry to entry, thus necessitating a schemaless database. Since we're going to be querying it a lot, I thought that a document database is probably the more appropriate choice than a key value store. So, the messaging app. In this case, I thought a key value store, particularly Redis, would probably be the right choice. We care a lot about speed because this is going to be had in real time with real-time conversations, and that it is very simple, and I probably want to replicate it around the world. So this is an archetypal use case for Redis. So question 6, the large e-commerce website. This one is difficult to say. Probably want to do a combination. If the inventory is relatively small, probably want to be doing a relational so you don't make promises you can't keep. But if your inventory is very large and you care mostly about response time, you probably want to do a Mongo or something like that. On the other hand, if you want to be driving product recommendations, perhaps you want to do a graph database, so you can keep track of what the user has ordered in the past and what they would be likely to want to order in the future. Might even do a combination of these. Depends on a lot of things, but yeah, we're not limited to one database. We could use several. So question 7, indexing all the websites on the World Wide Web. This one is a columnar database. The work is data intensive. Comparing values of columns matters more than grouping rows. The queries will benefit from text compression, and the values frequently change and will thus benefit from timestamping, both of which HBase provides out of the box. And we can and should define a uniform schema, right? We are the ones who are defining what we care about on the websites, not the websites. So we can thus define our own schema and operate it accordingly. This is thus an excellent place for HBase in particular. Question 8. This is the research grants. So anytime you're working with something that is literally a document, it's probably a good use case for a document database. We need to support a variety of data shapes, necessitating a schemaless database. Since we care about the ability to query the contents of the application, we probably want to do a document database rather than a key value store. Alright, question 9. We are building a database for Twitter. So usually social networking sites are the archetypal use case for graph databases, but since our dataset is so large, we can't. We need a shard, it's simply not going to work. Thus, we need to choose between a document and key value store. You could make a reasonably strong case for either one. In my opinion, since the data is relatively simple, and since we probably care a little bit more about speed here, I would go with the key value store, probably React. Question 10. Designing a database for all of your applications. Don't do this! Remember part 1 of this presentation. There is no universally good tool. Everything depends on your particular use case, and there is such a wide variety of applications being used in this company that there's not going to be one database that's correct for all of them. So yeah, everything's a trade-off. Avoid this way of thinking. It is toxic for your development success. So this presentation was based on one originally developed by my mentor, Dale Allishouse. His original presentation is available here. Once again, you can click on this link by downloading this PowerPoint presentation at the link available in the description. And if you would want more information about Dale or some of his work, feel free to visit his blog at Hideous Humpback Freak. Here are all of the resources I used in creation of this presentation. And that is it. Thank you very much for watching. If you have any questions about this presentation or others, feel free to drop a comment on this video or email me at howard.reith@gmail.com. Have a good one.